Okay, guys, and so I'm at some training this afternoon, and so we'll do our lesson on the video. Today we're going to kind of continue and expand on what we talked about yesterday with the atomic mass and calculating the average atomic mass of an element. That answer key is on my desk, so if you want to check your worksheet against my answer key, you can do so. Make sure that you understand how those problems work. I've worked them out, and so the work is there. But you need to make sure you understand how those problems work out because you'll see those on quizzes and tests for this unit. What we're going to do today is we're going to look at where's those numbers come from. And so how do we know that 90.5% of neon is neon 20 and 9.5% of neon is neon 22? Where's that data come from? That's what we're going to look at today, is where's that data come from and how do we get it, and then how do we read it? And so that's what we're going to do today. So you want to get your notebook out. If you don't have your notebook out, you might want to pause this and grab your notebook. But you're going to take a little bit of notes today. And so what we're doing today is we're looking at mass spectroscopy, or for short people call mass spec. Mass spectroscopy is going to allow us to look at materials based on their mass. That's what we're going to be looking at, is based on mass. And so let's look at neon, for example. So neon, we have two isotopes of neon, neon 20 and neon 22. Now they obviously have different masses. Neon 20 has an atomic mass of roughly 20. Neon 22 has an atomic mass of roughly 22 AMUs. And so how do we know that 90% of neon is neon 20 and 10% of neon is neon 22? Well, we figure that out via a mass spectrometer. And so let's talk about how that works. So the first thing we're going to have to do to our sample of our elements is going to be to ionize it. And so we're going to have to ionize a sample of neon. And if we take a sample of neon, it's going to contain both neon 20 and neon 22 because it's just natural out there that neon contains both. And so we're going to take a sample of neon and we're going to ionize it. Now, if you remember back to middle school science, you probably learned this little thing about the atom where you have the nucleus in the middle, and then around the nucleus you have these energy levels which make up the electron cloud, and the energy levels contain electrons. And that's a horrible circle. That's okay though. So to ionize, what we're going to do is we're going to shoot electrons at the atoms. Now, some possibilities. Remember, talk about how the atom is. Most of the atom is empty space. It's emptiness. So large likelihood that we're just going to pass those electrons through the atoms and not going to do anything. Or potentially, the atom could grab a hold of it, and so maybe that electron gets stuck in an energy level. Now, if we get that neon, say this is neon 20, so neon 20, and we have thrown an extra electron on it, well, now it becomes a neon ion, neon 1 negative. It's possible also that maybe we can knock some electrons off, and if we knock electrons off, then it would be positive. But we're just going to assume it's going to grab an electron and become negative. And so that's what's going on here, is we're going to ionize the atoms. And so we're going to get a sufficient number of neon 20s and neon 22s that become ionized. So they obtain a negative charge, if you will. Now, so what happens? Here's what happens. Oh, actually, let's back up. Let's backtrack for a second. Let's say that I gave you a tennis ball, and I rolled it, and I gave you a bowling ball, and I rolled it. Now, let's say you wanted to change the direction of those two balls, and you wanted to make them bend and turn that way. Which would be easier to make it turn? Okay, so you should say the tennis ball will be easier than the bowling ball because the tennis ball has less mass, so it's easier to turn than the bowling ball. And that's just the physics things. Physics, for an object in motion will stay in motion until acted upon by an outside force. Law of inertia, law of momentum, and so it's going to continue going in that direction until something makes it not go in that direction. So that relates to mass spectroscopy. And so let's hold that thought in your head here for a second. All right, so we have a mass spectrometer. It's just an instrument that does certain things. So first there's this ionizing chamber, and that's where we're going to shoot those beams at the sample. So we'll put our sample in here, and then we're going to ionize it, and then we're going to run that sample through an accelerator. It's going to go through a tube here basically. And this accelerator is going to then accelerate those particles. So they now have a negative charge, so we're going to basically pull and push on that negative to move them along this tube. We're going to use those charges to push and pull and move them along the tube. And they're going to be going pretty fast is what they'll do. And so now that's where that physics comes back into place. These particles are moving down this tube. Now, unless something acts upon them, they're going to move in a straight line, right? But this tube is going to turn. It's going to curve. And so we're going to have something act upon those particles in order to get those atoms to curve with the tube. And what we're going to do is we're going to put in this turn an electromagnet. Now, it's an electromagnet and not a regular magnet, because regular magnets have a constant magnetic field. Electromagnets, we can adjust the field. The more electricity we pass through it, the more magnetism it exhibits. The less electricity, the less magnetism. So if this electromagnet is off, there's no magnetism, and these charged particles will just flow down here and they'll hit the tube here. Now, if we turn the magnet on, we can adjust the field, stronger or weaker, and these neon particles, neon 20, that's charged, or 1 negative, not positive, and neon 22, that is charged, we can cause them to turn effectively. Now, which will turn easier? Think back to the bowling ball and the tennis ball. The one that's lighter is going to be easier to turn. So if we just turn our magnetic field up a little bit, we'll get the neon 20. I'll do that in green. The neon 20 will bend down the tube, whereas the neon 22, we'll do that in blue, because it's heavier, it's not going to bend as much, and it's actually going to hit the edge of the tube somewhere. Now, down here at the bottom, we have our detector. And what it's going to do is it's going to detect how many atoms are coming through here. It's just going to be counting, basically. How many atoms come through here? And the strength of the field, how strong we turn the field, determines which one of these comes down. So we set it to the field where it brings down the neon 20, and we're just counting. Here's a counter. It just starts to count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so forth. It just begins counting. Now, after we run that for a little bit, what we'll do is we would actually adjust the field. And so let's erase this. So the green was the neon 20. And so neon 20 was green. And now we're going to make the field stronger. Now what's going to happen is that with the field stronger, that light element is going to get pulled too hard, and it's going to come and collide with the wall somewhere. But the heavier isotope, the neon 20, instead of hitting the outside wall, is now going to come down the tube and hit our detector, and it's going to start counting. 1, 2, 3, 4, 5, 6, however many it's count. It's going to start counting. And so you have this detector counting based on the strength of the field, what mass is coming through. If the field strength is set at a certain strength, it's counting a mass 20. If it's set at a different strength, it's counting a mass 22, or whatever mass you want it to count. It doesn't really matter. And so what happens is you get a readout, a computer readout that, let's start at 17. So these are your masses. You'll have a computer readout, 17, 18, 19, 20, 21, 22, 23, and it just goes, it can go from 0 up to really, really heavy. And it's going to just throw out a graph. It's going to say, okay, we didn't get any hits, so here's 0 hits, and then here's, just some number. It doesn't really matter up here. You can do infinity. We got 0 hits at 17, we got 0 hits at 18, 0 hits at 19, and we got a whole bunch of hits on 20. And so it just makes a big peak. And then we didn't get any hits at 21, but we got some hits at 22. And we make another peak, and we don't have any hits at 23 or 24. And so that's the data that neon would give us. Now, what you then do with that data is you simply do an analysis of it. Okay, the bigger the peak, the more hits. The smaller the peak, the fewer hits. And so you just take that and you calculate the area of that peak. Calculate the area of that peak. Now, if it's neon, we're going to make our data fit. If it's neon and you calculate the area, you should get some unit around 9 units of area, whatever you calculate your area to be. And your units of area here at 22 would be 1. Now, what is the total area of your elements? Well, if you add up all your elements together, you had 9 plus 1, you had an area of 10, a total area of 10, which makes this area 9 over 10. It was 90%. 90% of your atoms that came down that pipe were this one, and this was neon 20. So neon is 90% neon 20. Whereas 10%, 1 divided by 10 was your total, came down this one, and so it's 10% neon 22. And that's how a mass spec works. It's a really simple, elegant little device. And so then you would do your calculations. Well, it's 20 mass times 0.9 plus 22 times 0.1 equals the atomic mass. And that's how you get your atomic mass of elements. And so what you're going to do is you're going to work with a little sheet of paper that's basically got a mass spec printout of an element. I'm going to want you to calculate the areas of each peak. Now, the peaks that I've given you on this sheet are effectively triangles. They're triangle peaks. And so your area of a triangle is 1/2 base times height. So that's going to calculate your area. So you'll calculate your areas, and actually you have 10 peaks on your graph. Calculate your areas, and you're going to need to total up your areas to get your total, this number right here, that you're going to divide by. So you'll take each area divided by the total area to get the percent of that individual peak. And then you can get all your percents. You're going to run through your atomic mass, percent times mass, plus percent times mass, plus percent times mass. And I think you have 10 peaks on this particular graph. And then you'll get your average atomic mass. I want you to write that average atomic mass down, then go to the periodic table and figure out what element this graph is representing. It's real data from a real element if you ran it through a mass spectrometer. And so it represents a real element. So hopefully that makes sense. If it doesn't, you can always pause, rewind the video, watch it again. Y'all can work in lab groups. You can go to lab tables if you want to. Just keep the lab tables clean and organized when you leave. Or you can work at your desk, however you want to do so. But you should have this finished before you leave class today. Okay? I will be back tomorrow, and we will just continue. Talk to you later.